All right, recording is rolling. It is Monday, October 31st, Halloween, spooky. And we got this list of fun activities to do. Oh, top scientist, top scientist. Here's top scientist for, so jump on the floor, gravity, orbit. Yeah, so if you're on this list, then good job. You guys did really good on that one. Oh, you know what, too? Over the weekend, I did get your papers back in your folder. Everything except for the last lab, I'm still working on grading those. Right? But if you want your last quiz back, then when I set you guys up with this lab activity, the last 20 minutes of class, you guys can get that if you want it. Okay. All right, so we're going to give you some energy stuff. You guys know all last week we did conservation of energy. This week is week 2 of conservation of energy. So I have a really classic conservation of energy question here. And then you guys remember this 3-page packet? Okay, so we've done most of this. Today we're going to do a couple of rows. All right, so have that out ready to go. And then, last 20 minutes class is going to be pendulums back in the lab area. All right, so let's take a look at this question. Well, it's been up here for a few minutes, so we guys maybe solve this. Now, let's say it's supposed to take a ball and throw it straight upwards at 30 meters per second. How high is the ball going to go? Did anybody figure that out? Anybody solve that? Anybody solve that? All right, okay. I'm going to show you guys a few different ways to solve it. And of course, no matter how you solve it, you should get to the same answer, right? Right. So one way is you could go second by second and count. Here, guys, if you throw something straight up at 30 meters per second, how fast is it moving after 1 second? 20. Because it lost 10 meters per second, right? It's 10 meters per second per passing second towards the ground. All right, so it's going 20 meters per second upward here. How fast is going 1 second later? Now 10 meters per second upward. How fast 1 second later?
None.
0 meters per second, which tells you that you've reached the maximum height because that would correspond with that, right? Okay, so you guys see how it took 3 seconds to go to the top? Hey, do you guys think it's going to take another 3 seconds to fall back down? Well, let's frame this question a little bit differently. Suppose you go to the edge of a cliff and you drop a ball. They say, how far is it fallen after 3 seconds? Because that would also answer the question, wouldn't it? It's the same answer, right? And wouldn't it be, I'm going way back in the day. So this is like a few months ago. You guys remember the height that something falls is 1/2 gt squared if it starts from rest? That looks familiar, right? Oh, in fact, I remember a specific story that goes with this. You guys remember Paul Hewitt going into the mine shaft, drops the rock 5 seconds later? Like, how deep is the shaft? Well, let's see, it's 5 seconds squared times half of 10. It's about 145 meters deep. How'd you know that, college? You guys remember that? This is the same thing, except it's for 3 seconds. 3 seconds of falling. So I can say, how far to fall? Right. Now, we're assuming that we're on Earth, because if you change planets, the answer changes. But 10 meters per second squared, that's the surface of Earth. 3 seconds squared. 3 squared is 9. Half of 10 is 5. 5 times 9. 45 meters. Okay. So if you drop the rock at the edge of a cliff, falling for 3 seconds, it falls 45 meters, right? Or if you took a baseball upward 30 meters per second, it would take 3 seconds to reach the top, therefore also rise 45 meters, right? That's one way to solve it. Another way to solve it is here. If you're a little bit more formulaic, you might look at these equations. These are kinematic equations. This is a few months ago, right? You can solve this without ever solving for time. Like we figured out it must be 3 seconds up, 3 seconds down, but you can cut straight through that. Go to this very last one. Because if you throw it up at 30 meters per second, that's the initial velocity. At the maximum height, it is going 0 meters per second, so you know that one too. You know both of these. You also know that gravity is causing the ball to accelerate downwards at 10 meters per second squared. X refers to some kind of displacement, in this case, height, right? So let's try it that way. This is a different method. Could I go final velocity squared equals initial velocity squared plus 2ax? Let's see, final velocity must be 0 meters per second. Initial velocity, well, you threw it upwards at 30 meters per second. That's being squared, right? Plus 2 times, now if you throw it upwards, but gravity's pulling downwards, I should probably call gravity negative in this case. 10 meters per second squared, right? And displacement would refer to height in this case, to go from the speed to the speed, right? We're going to figure out what the height is, and would represent the maximum height, because 0 meters per second goes to. And so, guys, what's 30 squared? Is that 900? 900? Can I subtract 900 over? Go negative 900 meters squared per second squared equals 2 times negative 10. That's negative 20. meters per second squared times the maximum height, like that. Okay. You guys see I can find height by doing that divided by that. So negative 900 meters squared per second squared divided by negative 20 meters per second squared. And so all the units cancel except for meters, which is good because I want some kind of height. 45 meters. That's the same thing as before, right? So doing it this way, counting the seconds, we got 45 meters. Doing it this way, third kinematic equation, got 45 meters. Okay. So there's two different ways to do it, but those are both the old ways of doing it. Now, last week I gave you guys a completely new framework. So let's think the new way to think about this. Okay? So go back to, you throw the ball straight up. Now the ball right here is near ground level. We're going to call it basically ground level, which means it doesn't really have any height, but it does have a huge speed leaving your hands, which means it has what type of energy? Kinetic. Right. And then it rises to, at the very peak, it has zero speed if you throw it like straight up. Right. So it has no more kinetic. Where did all the energy go? It went into what? Potential energy, gravitational potential. Right? Guess we have a ball Earth closed system. There's a closed system consisting of the ball and the Earth, right? Pulling on each other. Right, so I'm going to go sum of energy initial equals sum of energy final for a closed system, ball Earth system. And you guys just told me that this is kinetic. What's the formula for kinetic? It's on that poster hanging from the ceiling. 1/2 mv squared, right? Where this v is like throwing speed, right? Of course, it immediately starts slowing down right after it leaves your hand. Right? And then at the top, it's all potential energy, mgh, gravitational potential. Right? You guys know we're solving for this h, right? Right, good so far? Okay. Oh, I never gave you the mass of the ball. Is that okay? Do you need the mass? No, right? Because it doesn't matter what you plug in for the mass. You can plug in 1 kilogram or 5 kilograms. You're always going to get the same thing for h. In fact, if you want to, you just cancel it out at any point. You know what, let's solve this in terms of variables because we can do this in one step. Guys, what's the one step you need to get an expression in terms of variables? Divide the g down. You guys see divide by g? So the height, I'll swap the left and right while I'm at it. Okay, so I got the throwing speed thing squared. I got divide by 2, and we got to divide the g down. You guys see that expression right there? Right. Now you have an expression where you can get the height of any ball. As long as you know how fast you threw it straight upwards. Oh, and the gravity of the planet. I see. Now you can switch planets, and you can still give it an expression, right? So let's plug in some numbers. Now you guys know what the answer to this is, right? This is going to come out to 45 meters. As long as they plug in, I threw it at 30 meters per second. Right, and gravity's pulling down at 10 meters per second squared, right? So I got 900 divided by 20. So that's 900 crazy units divided by 20 meters per second squared. Height is indeed 45. The unit is meters. Yeah, look at that. That's the same thing we were getting using the kinematic approach, right? That 45, that 45, is that 45 meters. It's all the same thing, right? And this is, of course, the new way we're thinking about it. Okay, you guys good with that? All right, so I think that's a pretty good review coming back from the weekend for conservation of energy. Okay. Let's do next thing on this list, conservation of energy table. All right, so we did all these are all sum of energy initial equals sum of energy final. Well, there are a couple of open systems, so, but besides those, right, these are all closed systems, right? We did all those, right? And then we did this one. Now, let's review this one real fast because it's also very similar to the next setup. Okay, so the last one that we did in this packet involved, let's say there was a spring, there was like a ball being pushed down on the spring. The force it would take to press it down is equal to kx, but the energy stored is 1/2 kx squared, and that's what you care about for this new framework. Okay, then we let this thing go. Pow, shoot straight up. Okay, and at the maximum height, it would have all gravitational potential energy. You could set these equal to each other, and you could solve for things. For example, if you measured the height that it went to, and you knew the mass of the ball and how much you can press the spring, you could solve for the spring constant. All right, how stiff is the spring right here? Or if you do the spring constant, you could calculate what the maximum height would be. Oh, okay, so there's lots of things you can do with that. But the question I asked is what's the speed at the very top? In this case, you guys told me it was 0 meters per second. All right, you guys ready for the next one? All right, this next one is very similar, except it's just in reverse. Now I have I don't know, I might have changed the ball with a block, but whatever. Right, so it says a block on. it's going to fall and smash the spring. So do you think it's probably the same set of objects in the system? Instead of ball, I'm going to say block because I use the word block. Oops. Right? I care about the Earth because the Earth is pulling with the gravity force and there's a height change. Okay, and the spring because it looks like the spring is being smashed, being compressed. Okay, so point A is here, point B is here. So what type of energy up here? It has a height. Gravitational potential energy. Can I call it MGH? Throw a little subscript A on that, match that one. Right? Sure. Right. And then when it smashes that spring, okay, well, there might be a few different interpretations of this. Here, I want to point out this little detail in parentheses. See where it says assume no mechanical energy loss during collision, right? The next topic we're going into next week is going to be collision physics. So there's a little bit about this that I haven't told you, but usually you ignore it anyway for this type setup, right? Or if you say that the spring itself has very small mass compared to the object falling on it, you can basically ignore the collision physics, right? But do you think it's possible that all the energy at some point goes into smashing the spring, especially if it's like maximally compressed at some point? You can call it like 1/2 kx squared, right? You can set those equal to each other and again solve for stuff. It looks like does not look like the reverse of the previous one. It sure does, doesn't it? Right. Tell you what, if you're thinking really deeply about this, because when I designed this table and the way we're going through this, I'm trying to keep it like forest for the trees, pretty big picture. Right? But yeah, if you want to think more deeply on this, do you guys think that this compression distance is part of the height drop? Like, yeah, if the spring's being compressed vertically, gravity's still pulling on it, which is included in this H. So the H it goes from the very top to the lowest point it ever goes. Right? It's all embedded in that H, including the X. Another thing, we're talking about maximal compression, which would be different from equilibrium compression. So if I have a spring, I just rest this on it, right, very nicely, it comes to rest. That's different compression from if I drop it and like smashes maximally, which is what I'm talking about here. Right. Anyway, that's little details that you might run into one day, especially if you take physics in college. Right. But how about the answer to this question? What is the speed of point B? The way I've set this up? Looks like it's probably gonna be what? 0 again, right? Just for the speed of point B. Okay. And maybe more interesting questions you could ask, but that's the answer to that question. Right? You guys good? Okay. And here's what we do. We got 2 examples left. I want to cover this one today, and the asteroids I'm going to save for a different day because there's like a whole story and lots of detail. So we're going to save the asteroids for a different day. Right? But this one here, I've got a ball rolling without sliding down a hill of length L. Right? Now, this also involves some physics that we haven't talked about yet. We'll either do in December or January, depending on how the time plays out. Right? But I have the ball. I care about the ball. Right? So I'm focused on the ball, like rolling down the incline. Okay? I care about the Earth because there's a height change. Right? There's a height change. The Earth is doing some work on the ball, pulling it down. Okay? And one more thing. If there was no friction, that's to say, like if this was an air hockey table and you tipped it up, the ball would not actually roll. Right? It would look really weird. It would just like slide down with no friction. Okay? For it to be rolling, there must be friction. If it's rolling without sliding, it's static friction. Right? So I'm going to also include the surface of the incline. I'll just write incline. You can write ramp, incline, surface, right? Because that would be providing a force that would inducing the rolling. Right? Now, it's a different kind of friction than the 2 open systems that we looked at before. Like the kid in the sled sliding down this hill or this car break into a stop. Because both of those types of friction pulled energy out of the system, right? This is not that case. If it says rolling without sliding, see, like if I have another incline out here, like it could roll up an incline, this ball could do this. And it can do that forever as long as there's no energy leaving the system, right? So the energy is like still conserved. So this friction force on surfaces acting as a conservative force, not a non-conservative, right? Anyway, little details to think about. Yeah, we're going ahead. So what kind of energy do you think of point A? Gravitational potential energy, or potential energy, MGH. So subscript A on that H, match that one. Oh, good. Okay. And that's all we got. Started to rest, let it go. It rolls down. Right. Hey, at the bottom, do you think if you pointed a radar gun at it, it's going to read a speed? So it has some kinetic energy. So something to do with like 1/2 mv squared, right? Where the V would be the radar gun reading. Okay, so we got that. Okay. Now, here's where we're going to extend this concept a little bit, say plus, because there's another energy term that I haven't told you guys about yet that I'm about to right now. Okay. So Turns out that some of the energy will also go into making it rotate, making it roll, right? And different objects will roll differently. Could you imagine if I have a bowling ball up here, like a solid bowling ball, versus, oh, let's say a hollow basketball, versus like a solid cylinder, like say like this guy here, like rolling down. Suppose there was like a three object race, got a bowling ball versus basketball versus this pretty well solid cylinder. Do you think they're gonna finish differently? Like somebody's gonna win the race? Ooh, do you think they're probably gonna be going different speeds at the bottom? They will because their masses are distributed differently. Okay? So I also need a term to represent rotational kinetic energy, and it goes like this: 1/2 I omega squared. Okay. And so what the heck is this? Right. Well, see, it looks pretty well the same form. Actually, you guys know what omega is, right? Because if you knew the radius of the rolling object, you could connect that back to V. Because isn't omega just V divided by R? Or if you like, you could say V is equal to omega times R, right? You can go back and forth, right? So you can do some kind of substitution. This V and this omega are related to each other. They are related to each other, right? Based on the radius of the rolling object, right? But what is that I? Well, you can see structurally that I sort of takes the place of the M. You guys see that? Right? It's called rotational inertia. So this is like a property of rotation. So like the basketball versus the bowling ball versus the solid cylinder, the fact that their masses are distributed differently. Okay? Hey, you guys ever ride a bike that has like huge tires? Like a standard size bike tire is like 26 inches usually, but sometimes you can find one that's like 29-inch tires. Right? You guys ever ride one of those? Right? It's hard to get it going, but once it is going, it's really hard to stop it too. It'll like roll up on sidewalks and all that. Right? So that's like really big wheels will have like a larger I value than smaller wheels. Right? Anyway, just get you guys thinking on that. Right? So we're not going to solve this one today. I'll just leave it there. I'll leave the setup in place. Right? But in the future, again, like either December or January, we'll be able to go through and actually finish this problem. Okay? You guys good with that? All right. So we are done with this and we're moving on to the last activity. Now, the setup's going to take a few minutes, but then I'll have you guys back in the lab area. So it's going to be all good times. Right, so look at this pendulum here. Got this pendulum swinging. You guys can see swing, 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 swing. Right? Oh, and the fact that there's a height change, that kind of reminds me of the Galileo problem where went to the top of the Leaning Tower, had a height, he dropped it, maybe there's like a speed bottom. Right? Hey, I wonder, what is the speed of this bob at the bottom? Right? That would also be the maximum speed of the pendulum, wouldn't it? Like maximum speed. Right? So we're gonna drive this all fancy like, and then you guys get back in the lab area and you guys get to do some measurements and calculations and to see how this all plays out. Okay. So let me redraw a pendulum. I'm gonna get a vertical dashed line for reference line. Okay. All right, let me pull this pendulum back to let's say like right here. All right, so this pendulum's swinging. Right. You guys see this pendulum swinging, right? Yeah. Right. So something to do with that. You guys see. You guys see that? Right. And at the bottom, it definitely has a speed that I'll call V for velocity speed. Right. And actually, that would be the maximum speed, wouldn't it? Okay. So I wonder what that speed would be. Oh, yeah. As a function of how long the pendulum is, L, and also what angle you pull it at, theta. Right? Is that right? So hold on to the idea. We're gonna move around this a little bit. Right. Let's do a classic conservation of energy setup, which this is ultimately going to feed into. So this framework. Okay. So I'm going to say the sum of energy initial equals the sum of energy final. Right? Okay, so we're going from initial to final, right? Point A to point B. Right? Every single one of these steps we did had a point A and a point B on it. Right? So same story here. Point A, point B, right? And I definitely see some kind of elevation change. Like the ball used to be at this height, and then at the very bottom, it's down here at this height, right? You guys see like some kind of height change right there? Right? Call it H, right? You guys see an H, right? Right. So what type of energy does it have at the endpoint? Potential, gravitational potential. Can I call that, what are we about to write? Right here? MGH. Yeah, MGH. Right? Okay. Now at the bottom, let's see, it's definitely in motion. And if I define this as height 0, that means it has no more gravitational potential, which means it's all what type of energy? Kinetic. which is your 1/2 mv squared, isn't it? You see that? Okay. And the question that our target question, our goal is to figure out what is the speed. So we're trying to figure this out. Is that true? Right? Good so far? All right. Let's go ahead and solve this. Let's see how far we can get. What's going to happen to the mass of the bob? Aha, cancels out. Or you can just plug in whatever mass you're using, but it doesn't matter what it is. It's not going to change the answer anyway. It cancels. Plug in like 0.2 kilograms or whatever. Right. So, I see 2 algebra steps to get to the answer in terms of variables. Can I cross multiply the 2? So v squared is 2gh. That would be true, wouldn't it? Right. And then what's the last algebra step? Square root. And say the speed that's going at the bottom is the square root of 2gh. Is that okay? Hang on. Where have you seen that before? I think you guys have seen that probably at least 10 times in the past, right? Including last week. You guys remember the Galileo problem? Galileo drops the ball, point. Hey, the speed square root 2gh. Right? This shows up over and over and over in physics. Right? It's going to come back next semester too when we're doing like Bernoulli principle and fluids. Right? Yeah. Right. So here it is again. Right. So pendulum, different looking setup than Galileo dropping the ball vertically, but hey, it's the same answer, isn't it? Right. Right. Now, I guess if you could somehow, you could probably like hold a ruler up to this or a meter stick and try to estimate what that height change is. That's really hard to do, especially if it's kind of a small angle, like 10 degrees or something. It's like, I don't know, it's like a centimeter or something. Right? But you can much more accurately calculate what h is. But we have to dig into some geometry. Right? You guys ready for a fun geometry adventure? Right? Okay, can you calculate this h based on this L and this theta? Right? You guys ready for this? Right, so step you guys through step by step. Is this L equal to this L? Is that the same L? Same length, isn't it? Right? You see it? And wouldn't this height change be this full length minus this bit here, which is this leg of this right triangle? Ooh. You guys see a right triangle right there? And what is this leg of this right triangle equal to? What times what? L times the sine or cosine? Cosine. Oh yeah, cosine. It goes back to like what, first, second week of this class. Yeah, L times cosine theta. Okay, so wouldn't H then be L minus L cosine theta? Is it? H is L minus L cosine theta. True? Right? And if you want to, you don't have to do this, but could you factor an L out and say L times 1 minus cosine theta? Right? If you like it like that. Second. Right. Right. So now we have a very accurate H because it's easy to measure L with a meter stick. Just hold the meter stick up here. Right. And probably pretty straightforward to measure a theta too. I'm going to remind you guys how to do that. Right. But doesn't that feed in right there? Right there, just like that. So put it all together. Right. This V is this V, same V. We say V equals. Right, so V equals. Right, well, it's a big old square root. So big old square root. Right, 2g. And then instead of h, I'm going to substitute in this expression here. L times 1 minus cosine theta. Just like that. Isn't it? Shouldn't that be the speed? It comes from conservation of energy and some geometry right here. Okay. Okay, so if you know what planet you're on, the length of the pendulum, and the starting angle, the angle you pull it at. Okay. All right, here. Let me pause this. Pause. All right, recorded, resume. All right, so you guys good so far? All right, so I do want to remind you guys how to use the protractor, right? Because I see this come up today. Right? How do you measure how big this wedge is? Now, just eyeballing it, just look, I don't know, about 30 or 40 degrees, somewhere in there. Just eyeballing it. So I hope if I come up with about 30 or 40 degrees, then I probably got a number that's good to go. Right? And so what I'm going to do is take the node of the protractor. Right? I'm going to put this node right here. I'm going to zero out the vertical. Right? And then whatever angle I pull it to will naturally sweep through this angle. And it looks like about 34 degrees. that look like 34 degrees right there? Right, 0, 10, 20, 34. Like from the vertical, about 34 degrees. You guys see that? Can you guys do that when you get back there? Lab area? Right? You guys can do that, right? Right, everybody good? Okay. So when you guys walked in, this page was on your desk. So you guys got this page in front of you right now? Right. Now this page has 3 things on it. So let me just point them out real fast. On the back side are 20 conceptual questions related to work and energy. I might do a Kahoot with you guys, depending if we have time this week. So maybe we'll get to this. Okay. This one, do you guys remember that projectile lab with those spring launchers going out in the balcony, the whole deal? Right. Those are going to come back on Wednesday, and I'm going to have you guys do one more step, which is to calculate what is the spring constant based on where it lands and blah, blah. Okay, so that'll be Wednesday's adventure. But today, look at that. Got a little tiny pendulum here, right? And I got a table set up, right? Pendulum maximum speed lab. Okay, that's what we've been spending the last few minutes doing, isn't it? We're trying to figure out what's the maximum speed. Okay, so trial. See if you can get 3 trials. I think if you get a pretty good pace, you might be able to fit in 3. Let's do 3 trials. Okay. G, guys, what's the units for a gravity field? Meters per second squared. Is that right? Okay. If we're doing that, should it be 9.8 all the way down? Would be the number that you punch in your calculator for meters per second squared. Okay. Length of the pendulum. Length of the pendulum. Suppose, I mean, you guys can see some pendulums sort of set up back there from last classes. Suppose you get a little pendulum length of about, 62 centimeters. Does that look probably reasonable, about 62 centimeters? Okay. Guys, are you gonna, length is measured in meters, right? Are you going to write the number 62 here? Yes or no? You're right. You will not do that, right? Because 62 meters would be like the height of a very tall building, right? Like a multi-story building. Right? That's not what pendulums are. Okay. Guys, 62 centimeters. What number do you actually write right here? 0.62, right? Like if you have 62 pennies and I say, how many dollars do you have? Wouldn't you write 0.62, right? Right. So how many cents in a dollar? 100. How many centimeters in a meter? 100, right? Like centi. Okay. So 0.62 could be a reasonable number here, right? Okay. Theta. Let's measure the angle in degrees for a couple of reasons. One is that your measuring tool already measures in degrees. And the other reason is that as long as your calculator is also programmed in degrees, okay, so everything's going to be degrees, okay? So when you calculate cosine of an angle, as long as it's degrees, it's going to be okay, okay? So that you might get something like 30 degrees would be reasonable, 32, 34, 40. Okay? V calculated. Well, hey, if you know all these values, can't you calculate V? Isn't that what we were just doing right here? Ooh, look at that. Square root up. I started set up for you, didn't I? Can you guys take this and just copy paste it right there? I'll do it with you guys so that we all have it. 2GL times 1 minus cosine of the angle. Square root in that whole expression right there, right? So where the G is, you put 9.8. Where the L is, you might put like 0.62 or 0.75, something like that, 0.53. Okay. And then where the theta is, you'll put how many degrees? It might be 32 degrees, 40 degrees, 25 degrees. You guys do that? Right? And you'll get a calculated speed in meters per second. Okay, you guys got that? Okay. Then finally, I want you guys to actually get the empirical value. Okay, so the last 2 columns both refer to the same value, but different points of view. One is calculated. One, you're going to measure using the speed gauge. It's back. Speed gauge. You guys remember how to use this? Okay, so what I would do is dump this upside down, put it right here, and when the pendulum swings through, it's going to tell you. Okay, I didn't get it. Okay, let's try this again. So it's right here. Pendulum swings through, and it tells you exactly how fast in meters per second. Now that number says 0.99. You're probably going to get a number somewhere around there. It might be a little bit less than a meter per second. It might be up to like 1.5 meters per second, but somewhere in that ballpark. Okay, is that all right? Getting about 1/2 to 2 meters per second, something like that. Okay. And there's one more thing I want to tell you guys, which is I tried this over the weekend and it worked. I'm like, okay, so this all works, it's all good. But I think I may have been kind of lucky because today, I don't know why, but this speed gauge is really good at picking up my finger. When I swipe my finger through, I get a number. But it hasn't been able to register these lab weight materials very well. I tried like wrapping them in different material, like masking tape or something that didn't do anything. So here, if it helps, here's what you can do. If it's not registering it, you put speed gate here and it doesn't read it at all. What you can do is just hold your finger next to the pendulum, go as the pendulum's going, and then swipe your finger through speed gate side by side with the bob of the pendulum, right? And get a proxy number that's probably pretty close. Okay. All right, you guys good with that? All right. So you guys have the rest of class to work on this lab. Hold on to this paper because we're going to need it for Wednesday for this other lab. But I will be walking around helping you guys out. All right, you guys got 15 minutes. Ah, that's perfect. Perfect. Halloween.